Now let's do an example with our non-inverting operation amplifier. So here comes an example. Let's start with our non-ideal model. This is the non-ideal model, and let's connect it up in the non-inverting amplifier case that I showed you. So we want to define our gain this way. We want to find the circuit gain of this amplifier circuit, and the gain is defined as the output divided by the input. So let's use the node voltage method. And let's first consider this node A. So let's consider our currents that are going out this way, and we know that the sum of those must be equal to 0. So what voltage do we have here? V out minus what voltage is over here? That is A times Vp minus Vn, and divide that by the resistor R0. Now let's consider this value right here. V out minus this voltage is Vn, and we're going to divide that by R1, and that is going to be equal to 0. Now let's do our node at this point. We can say Vn minus V out divided by R1 plus Vn minus 0 divided by R2 plus, right here, Vn minus, going all the way, keep going, right there, Vn minus Vp divided by Ri, and this all equals 0. Those are the two values, these are the two equations, I'm going to call them the A equation and the B equation, that define the two nodes that we have. Let's also take a look at the circuit, see if there's anything else that we know, because at the moment we have 3 unknowns and only 2 equations. We don't know V out, Vn, or Vp. But if you look right here, you can see that Vp is equal to Vs because of the way the circuit is hooked up. So let's just substitute that back in for Vp in each of those cases right there to make these equations a little bit more simple. Now we have 2 unknowns, Vn and V out, and we have 2 equations to solve them. So in order to write those as a matrix equation and apply Cramer's rule, I've given you a little example here. You might want to just stop the video for a minute and take a look at the math of this example. I took the 2 equations right here and I converted them into matrix form for V out and Vn, and then I applied Cramer's rule. You may have to look that up online if you don't remember it from math, but stop the video right now and do a little bit of practice on this particular problem and see that you can get the answer for the gain of this op-amp. Okay, I'm hoping that you spent a little bit of time with that example and did the non-ideal case. That's the last time you're going to have to do the non-ideal amplifier in this class. Now let's rewrite our node A equation. V out minus A times Vn minus Vp divided by R out plus V out minus Vn divided by R1 equals 0. And here's the KCL node that I had at node B. Now let's apply our ideal op-amp equations. Remember, we know that Vs is equal to Vp, but we also know, because it's ideal, that Vp equals Vn. So if Vn equals Vp, then this is 0. Vn is Vs, Vn is Vs, Vn is Vs, and Vn minus Vp is equal to 0. Great. Our A equation and our B equation, we've applied that simplification. Do we need to apply anything for the currents? No, so we don't need to use that information. But keep your eye on this one. Remember that the output resistance is 0. We're going to need that. Right here, this equation kind of gives us the idea that we could solve for V out very easily, because the only values we have are V out and Vs. But remember that this value is 0, so it's like we're dividing by 0. This is not a good equation for us to use. Let's use the B equation instead. So for the V equation, I want to solve for V out. And I can say, right here, there's my V out. Okay? So I can say that V out is equal to Vs times 1 divided by R2 plus 1 divided by R1, and then I have a V out over R1 on the other side. So if I solve this, I can say that V out over Vs, that happens to be my gain, is, I'm going to multiply this thing out, R1 plus R2 over R1 R2, and then I'm going to bring this R1 over to the other side. See, this R1 came over here. So now my R1s cancel out, and my gain, which is my output divided by my input, is R1 plus R2 over R2. Awesome. If we actually calculate that for the numbers that we have here, the value is 5. If we had calculated it using the non-ideal case, it was 4.99975. So this is a very good approximation for an ideal op-amp, and this is how we are going to do our problems in the future. So remember that the circuit gain depends on the circuit. Here's the gain, we just derived it. Remember, saturation is going to take over too. We can't make this gain just as large as we want. It's controlled by the power supplies that we put on this op-amp. And again, back to our wild horse corral.